Okay, so off we go. Last time we talked a little bit, but not quite as much of a little bit as we're going to today. We previously talked about curl, right? So curl is denoted like this because of the symbolic, compact little symbolic formula that we can use to memorize the formula. It's very convenient. And what is the purpose of curl? Well, it's in a way tells you how the fluid represented by the vector field is circulating, rotating, spinning, twisting, however you want to describe that. So we saw one example last time, and that is for this, what I like to call stirred pot vector field, right? We see that the curl is computed to be 002, which points up. And notice that this fits the expectation. This pot, the water, is circulating around this vertical axis. And furthermore, in the direction indicated by the curl, in the sense of your thumb of your right hand pointing in the direction of the curl, your fingers circulate around your thumb in the same direction that the fluid is going. So this is how curl describes this sort of rotation of the fluid, whatever you want to call it. Okay, so that's where we left off last time. Note here we have the fluid is going. Let's see here. Let me just draw kind of like this. It's going entirely in these lines, and so you would look at this and probably think, nothing's really particularly rotating there. And as you would expect, the curl is 0. Okay, so here's a subtlety. A lot of students will connect these observations by saying, okay, the point here is that the flow lines are straight lines. The flow lines are not curving. And actually, that's not really quite the point. Let me show you another example that also has straight flow lines. So this vector field here, I'm going to leave it to y'all to persuade yourselves this is what this vector field looks like. You can see that the magnitude of the field vector depends on y. You can come over here and see that for bigger values of y, the field lines are bigger, etc. Note all the field lines point in the x direction. Again, as you can read from this algebra. So with that vector field, at a glance, what do you think the curl is going to be? Well, again, from the sort of tempting, sort of slightly incorrect point of view, you look and see that all the flow lines are straight lines. So it's tempting to say there's no curl. But then you do the calculation and see that, in fact, there is. The curl is actually 0, 0, negative 1, which points downward. So how's that? In what sense is this fluid circulating? How is there a rotation, apparently, according to the curl vector, apparently kind of clockwise as seen from above, according to our thumb and right hand? Well, here's the idea. If you were to drop a leaf onto the surface of the water here, imagine this vector field representing the flow of fluid, right? And so the fluid is kind of going this way over there, and it's going this way over here. So two different directions, and then it kind of meets stationary in the middle. What would you expect this leaf would do? And there's two things I think you would expect. One is you would expect the leaf to go that way, and that's correct. It would go that way. But there's another thing that would happen, and that is, notice that the leaf is being pushed harder on that side and not as hard on that side. It's being pushed more on what you might call its left side. And what happens if you push something more on the other side, more on one side than on the other side? Well, it's going to probably start to turn. Right? So I maintain, in fact, I'll just do this with my hands here. This leaf, as it goes this way, the leaf would be turning as it flows down whatever kind of river that is. Does that seem kind of plausible? I don't know if y'all can relate. I don't know if you've ever been on a hike and where there's a creek and trees and there's a leaf that falls in and you watch that leaf float down the creek. It doesn't just go and keep its orientation. It will tend to turn as it goes. And that's because the fluid, the water in that case, is pushing it harder on one side than on the other side. And so there is a rotational aspect to the flow, even though the flow lines are all straight lines. So, kind of weird. But anyway, this is one of the things curl is good for. Curl can anticipate, right, this object curl, by its not being zero, can anticipate actual twisting of the fluid, even when at a glance it doesn't really jump out at you as much as, for example, here it does. Okay. All right, so moving along, remember all of 3.4 is kind of premature. It's all sort of, we want to lay some groundwork and make some observations, some claims, really, and let you be kind of digesting and mulling, chewing on those ideas and kind of getting used to them until we get to chapters 6 and 7 where we're going to straighten a lot of that out. So here's something I want y'all to be chewing on. This is an oddly convenient observation. Turns out it's really convenient, really, and fundamentally natural to compose these operators, specifically in this order: gradient, feeding into curl, feeding into divergence. It's got to be in that order. And it turns out some really good things happen. So there's various ways to write this down. Some of the observations you can just write down in algebra. I claim that the curl of a gradient of any function is always zero, assuming nice regularity, no singularities, no discontinuities, no problems of regularity sort. Curl of a gradient, is always zero. If the divergence of a vector field is zero, then that vector field is the curl of a different vector field. Seemingly very, very different fact. But this and several other statements that kind of look like these, that would be very easy to accidentally confuse and conflate and get out of order, what have you. All of those statements can be viewed on this diagram, where we compose the operators in this order, as one single simple statement. And that is that all of the lifetimes, what I'm going to call lifetimes, and I'll flesh it out in a moment, all the lifetimes are 2. Let me explain what I mean by a lifetime. Okay, so by the way, this is just a metaphor. To my knowledge, I may have made this up. I'm not sure. It's possible someone told me this 30 years ago and I forgot and then remembered but thought it up on my own, right? That happens sometimes. Anyway, suppose you have a vector field. Suppose you take its curl. That gives you, of course, another vector field. I claim that if you were to take the divergence of that, you would get 0. This is what I call a lifetime of 2. I like to think of 0 as being death. It's just a metaphor, right? Don't look for deep meaning in this, but it's kind of nothingness, and no matter what you do to 0, it stays 0. Take all the divergences or curls or whatever you want of 0, and the result is always 0, right? All differential operators on 0 give you 0. So it's kind of like death. And I'm going to think of this as being kind of birth, and I'm going to think of this as what you might call survival. And so this little story here, birth, survival, death, the length of the lifetime is 2, in the sense that there were 2 operators applied before death. Again, it's just a metaphor. Okay, so I claim, again, the fact that all lifetimes are 2 allows us to draw a bunch of these conclusions. For example, if you have a function, here let me try to get all of this onto the screen at the same time. If you have a function f, if you compute the gradient to get a vector field, right? Take the gradient, that gives you a vector field gradient f. If you then take the curl of that resulting vector field will be 0. Okay, so here we go. We take the curl of that, we get 0. So you can think of, let's see if I can get this all onto the screen. There we go. You can think of this algebraic statement, this equation that explicitly relates curl and gradient. You can think of that as just a manifestation in this place on the diagram of the fact that the lifetime is 2. Right? Everybody see what I'm talking about there? Let's consider the alternative. The alternative here, if I had not gotten 0, if this had been something other than 0, if I had had a function and I took the gradient to get a vector field, and if I took the curl and got not 0, then the soonest it could possibly die would be there, and that would be a lifetime of 3. Not allowed. Lifetimes are all 2. Right? So the fact that you have to get, let's see here, the fact that when you have a function, you take the gradient, giving you another vector field, the fact that when you take the curl here, that you always get 0, is just a manifestation of this general statement that lifetimes are all 2. How you doing? Is everybody on board? Is everybody with me? Okay. Here's another version of it. Suppose you have a vector field and you take the divergence, and suppose you get 0. Well, from this diagram, I claim this, if this is where death was, well, then it has to have been born here. Said differently, there must be a vector field whose curl gives you that initial original vector field. Because this is then your lifetime, and it has length 2. All lifetimes have to be 2. Right? So both of these statements down here you can view as just being, again, special cases of this much terser, pithier, easier to remember, funnier way of thinking about it, which is that lifetimes are all 2. Everybody on board? Okay. So, very useful facts. We're going to use this information a lot when we get to chapters 6 and 7. For the moment, I just kind of want to plant these thoughts. I will point out, by the way, that this whole business about lifetimes being 2 when you compose the operators in this order might seem mysterious and unexpected and wow. I mean, it's an eyebrow raiser. Weird. Right? When things are weird, unexpectedly simple, like this, lifetimes all being 2, in a mysterious way, then that's a suggestion that, you know what, there's probably a lot more going on here than we currently understand. And in fact, that's the case as well. So, in fact, there are really a lot of connections between these operators, and this is just kind of the tip of the iceberg. And for whatever it's worth, when we get to and see a bunch of this in chapters 6 and 7, that also is only going to be the tip of the actual whole iceberg. This subject of divergence and curl and related facts is actually very, very deep stuff. And there are ultimately very simple reasons why all of these amazing facts, the ones that I've shown you here and many, many more, they're all ultimately very simple facts. It's just that they're very simple statements made about extremely complex and sophisticated things that we don't have the ability to discuss. Okay, so anyway. Okay, so that does it for chapter 3. We are going to move on now to chapter 5. Yes, I know I'm skipping chapter 4. Real quick, let me just talk about that. The reality is that chapters 6 and 7 that I keep making references to, there's a lot in those chapters. There's a lot of ideas. They're weird. There's a lot of connections between them. There's lots of kind of problem-solving techniques that you need practice working on, and there's a lot to be said. There's a lot to be digested when we get to chapters 6 and 7. Historically, it used to be that would get covered at the very end of the course. After all, those are the last sections from the syllabus. And so students would be learning all this very intricate stuff, and boom, class is over, final exam 4 days later. And this is not good, right? Students need more time to be able to digest those ideas. So anything from the course that isn't prerequisite to chapters 6 and 7 should come after chapter 6 and 7, so that we can move chapter 6 and 7 earlier into the course, and therefore so you have more time, as much time as we can possibly give you to digest chapter 6 and 7 before the final. So in fact, sadly, there is really only one part of the content syllabus that isn't prerequisite to 6 and 7, and that's chapter 4. So that's why we're skipping chapter 4 for the moment. We will come back and cover it after chapters 6 and 7. And it'll take us, less than a week. It's not much, but every little bit will help in terms of 6 and 7. Okay. Everybody okay? Moving on to chapter 5. Typo, by the way. I wrote here that partial derivatives are in chapter 3. It's wrong, of course. It's in chapter 2. Sorry about that. That was a typo. I'm going to get that fixed. I just haven't done it yet. So if you'd like, feel free to take your red pen and ink over that. That's chapter 2. So that said, the point here, the reason I'm bringing up partial derivatives is to remind you that partial derivatives, they get mentioned first because they're easy, because they're relatable. Partial derivatives are really not the fundamental point of view that you should have in your mind about multivariable derivatives, right? So the big tool, the fundamentally, when you leave this course, someone asks you, what is the derivative of a multivariable function? Your answer should be the derivative matrix. That's what a derivative is. It's the matrix that relates input changes to output changes, right? So the derivative matrix is the thing. Why don't we start with that most important point of view? Well, because it's weird and it takes some developing to get to it, and it's just a lot easier to start with partial derivatives. Okay, so we're in a similar situation here. We're going to be talking about a bunch of different points of view on multivariable integrals, several anyway, and well, I'm going to start with the one that's not really the best one, but I'm going to start with the one that's the most convenient, the most relatable, the most familiar, and the easiest. Again, it's just for foot in the door purposes. And so, again, the reason I'm telling you this, please don't hang your hat on this. Please do not set this as the cornerstone of your point of view on multivariable integrals. This is not a good cornerstone. Okay, so here's some old news. Rotated surfaces, finding the volume inside of the rotated surfaces. So if you want to compute this volume here, for example, we have an old math, Calc 2 point of view on this, which is that you take cross-sections, you take slices, and you argue that if I take all of those slices and add up over all those slices, the sum of those individual pieces of volume gives you the total volume. Okay, and then each one of those individual pieces of volume I can view as being a cross-sectional area, which of course is just the area of a disk. That's an easy formula, pi r squared, right? Interpreted appropriately to this picture. And then times the thickness. The thickness being, in this case, well, how thick that little thing is. Well, that's a little piece of the x-axis. That thickness is dx. So area times thickness gives you volume. And so these are the volumes that we're adding up in an integral on the x-axis. Hope that looks familiar to everybody, yeah? Okay. Alrighty, so we are going to kind of take the same approach, this fundamentally single variable calculus approach, to computing a kind of a multivariable integral question. I want to entertain now, suppose I have not a rotated curve, but suppose I have a graph of a multivariable function, such as, well, maybe a surface kind of like that. That's what a graph would look like, of a function of two variables. And suppose I want to compute the volume sitting under that graph. And of course I have to tell you, what my bounds are, and specifically I want to talk about under the graph and sitting over this rectangle. Everybody see the question we want to address? Right? We've got a graph, gives me a surface. I can talk about what's between that surface and this rectangle. Okay. Okay, so I'm going to take the same approach that we did on the other page. And I'm going to say, yeah, I can take this loaf of bread and slice it up into little slices of bread. Right? And I can argue that the volume of that slice is, it's tempting to say, let's compute this area and multiply times this thickness on the y-axis, that little thickness dy. Wouldn't it be nice if I could do that and say just cross-sectional area times thickness? Well, here's the problem. Up here, when we tried to do that, our cross-sectional area was a disk. Barnyard variety, old formula from, middle school or something, right? The area of a disk, pi r squared, old news, easy formula. This shape, this cross-section, it's not a rectangle, it's not a square, it's not a triangle, it's not a disk, it's not a trapezoid, it's not one of these formulas that we know previously, right? So there is a temptation to, at this stage in the attempt to just kind of bail and say, yeah, this isn't the easy formula that it was in the rotated case, so I don't know, I guess we have to bail here. Everybody's on board with that? Okay. All right, well, here's the thing. It is true. This is not a middle school geometry familiar figure. However, it is still kind of familiar. After all, it is the area under that curve. And that phrase, area under a curve, rings some bells. Right? So we're actually going to be able to compute this area, what I'm going to call this cross-sectional area. We're going to be able to compute it because it's the area under a curve, and we know we have a tool called integrals for computing the area under a curve. Okay, so proceeding on the next page. Here's that curve. I want to compute the area sitting under that curve. Now, wait a second. If you're going to compute the area under a curve, that curve needs to be a graph. Oh, good news. It is. It is the graph. It's described by that equation right there, which is a graph. Problem is that looks like a graph, which is a surface, not a curve, and it kind of is. But in fact, we can make it a curve as follows. Notice what I am specifically looking at. I'm trying to find the area of this cross-section where I fix y as being this value, whatever that value y is, defining where I'm looking at the slice. I'm interested in the area for that single value of y. Said differently, y is fixed. Said differently, y is not a variable as we do this calculation. Y is now a constant for the purposes of that calculation. So, if I want to talk about what happens when x, wrong color. If I want to talk about when x goes from A to B, right? So x goes from A to B, fine. Well, that's going to make then this point x comma y, conveniently y is of course fixed, x comma y, these blue points just go right exactly where I want them, right under this curve under which I want to compute the area. Right? So I can compute that area, no problem. This curve is a graph. It's the graph of this function where x is a variable, y is a constant, allowing me to take x comma y and plug them into f and get heights, and thus this curve. How are we doing? All right, so let's flesh out that area then a little bit more. Here we go. This area that I'm trying to compute. Messed that up. Anyway, that area I claim is this integral. I'm going to be multiplying heights, which are z, which of course are the value of the function, multiplying heights times widths. These little widths here, I didn't draw that well. Let me do that again. These little widths are little pieces of the x-axis, dx. And so height times width, f of x comma y dx. That's what I add up as x goes from A to B. And that gives me that cross-sectional area. So it's a little bit more work than just saying pi r squared, right? But sure enough, we now do have a formula for the cross-sectional area. So we are in business here. We can totally write this as cross-sectional area times thickness dy. And here's those details. Now I'm going to have to wipe the colors off of here because my picture's getting cluttered. So apologies, but I got to get rid of all this stuff. Cross-sectional area is what I multiply by thickness dy, and that's what I add up. Let's see here. Let me do it again. Let's see. So cross-sectional area times thickness. Oh, come on. Thickness dy. That's what I add up as y goes from C to D. What do you say? Does everybody buy it? All right. So, yeah, works just fine. A little weird, but works just fine. And so this expression here will indeed compute that volume. Now, just a couple of things to observe. Here we have an integral inside of another integral. That does seem weird, but it all makes sense in context. For what it's worth in terminology, this is called an iterated integral because you're taking an integral of an integral. I quibble that, yeah, it is too. It's an integral of an integral, but the integrals are different. We have a dx integral and then a dy integral. It's not the same thing being repeated multiple times. To me, iterated means the same thing being repeated multiple times. It's just not what we're doing. So I don't think this term is quite right, but this is the very common term that practically everyone uses. So we'll go ahead and use that term here for whatever it's worth. I like the term nested integral because it's an integral inside of an integral, just like nested boxes or nested dolls or whatever. Okay. Another little terminological thing. There's a temptation to refer to these two separate integrals as, well, there's the first one and there's the second one. And it does not make sense is the problem. Because as you're developing the integral, the dy integral is actually written first. Right? We wrote down the dy integral first and then made a subsequent argument about that cross-sectional area. We wrote the dy integral first. However, when you're evaluating, I have to evaluate the dx integral first. After all, that dx integral is my integrand for my dy integral. I can't compute the dy integral. I don't even know it's integrand yet. Right? So, this is weird. When you say the first integral, I don't know what you mean. Do you mean the one that was developed first or the one that's the one that's evaluated first? It's ambiguous. Not clear. So, my advice, use the terms inside. I know what you mean by the inside integral. Couldn't be more clear. In this case, dx is the inside integral. And then outside. In this case, the dy integral. Inside and outside. That is clear. Okie dokie. Very importantly, don't forget the roles that the variables are playing for these different integrals. And this is it's an easy thing to lose track of. Let's talk about this inside integral right here. All right, notice I didn't say first or second. I'm talking about the inside integral. X, of course, is a variable. Of course it is. Right? X is going from A to B, like that. But don't forget, as we do that, the whole point to this inside integral is that we're computing this cross-sectional area. In order to talk about that cross-sectional area, I need for y to be fixed and therefore to be constant. So, as I've got it written down here, notice that it's the outside variable that is constant as you compute the inside integral. All right, so now I've written this particular integral with the dx integral inside of the dy integral. That's how we developed this one. We're going to talk in a few minutes about what happens if you do it in the other order. Everything changes, right? So which one's on the inside, which one's on the outside, that'll all change. But what is always the case, no matter how you order your differentials, the outside variable is always a constant for the purposes of the inside integral. That's, again, very important to keep track of. Okay, with all of that noted, let's do one. Here we go. I've got here a graph. Taking the graph of this function here. Y'all remember what this graph looks like. Of course, it's a paraboloid. And I want to know how much volume there is under that paraboloid sitting over this rectangle here. I'll talk about that notation in just a second. And so kind of a weird situation though I want to recognize. I'm not going to draw my whole paraboloid. I'm not interested in the whole paraboloid. I want to know just the part of that paraboloid that's sitting over this orange rectangle. And so that relevant part of the paraboloid, well, it's just kind of, I don't know, it's a hard thing to visualize and draw. But imagine that there was this paraboloid like that, and this is the part sitting above that rectangle. I hope that makes sense. Okay, but again, we don't want the rest of it. Okay, want to find this volume sitting under the surface over the rectangle. All right, let me talk about the notation here. What is the deal with this notation for this rectangle? Here's the rule. This notation, you see the times there. I know that looks kind of like a cross product, and yeah, sadly, it's the same symbol. But in this case, because it's intervals that are between the times is between, this notation means that the left interval from 0 to 1 is the range of values of the first variable, which is x. The right interval here, 1 to 2, is telling me the range of values for the second variable, y. And I argue that if you know you're looking at points whose x coordinates are here and whose y coordinates are here, this rectangle is the rectangle that's defined by those constraints. Does that make sense to everybody? It's a very convenient notation. We're going to use this a lot, so heads up, be on the lookout for that. It's just notation. Okay, so that said, find the volume under the graph. We've already argued about iterated integrals. We know the answer is that the volume is going to be an iterated integral. Here it is. I didn't really do anything here. I just I interpreted from the previous argument, a page and a half worth of argument that I don't need to repeat. And now we compute. Again, we have to start with the inside integral. How am I going to compute that inside integral? Again, don't forget the outside variable, y, is constant. See, y is our outside variable, so I'm going to treat y, and therefore y squared, for example, as being a constant as we compute the inside integral. Easy to lose track of that. Notice how that plays out in this integration. I take an integral here. Apparently we're taking an integral and looking at this term y squared. A lot of students will see a y squared and think, oh, integral, oh, power rule, and we'll write down like 1/3 y cubed. Right? You can see how that would be an easy mistake to make. But don't forget, again, y is a constant. Wrong. y squared is a constant. And when you're taking an integral of a constant, you just get that constant times the variable, of course, being x. So the integral of y squared here is x times y squared. Is everybody okay with that? Everybody's happy. Easy landmine to step on. Don't write down 1/3 y cubed. That's totally wrong. Misinterpreting what the expression means. Okay. So let's look at the other term over here. We've got, let's see here, this x squared. X squared. Well, x is my variable. So x squared really is a power rule problem, and the antiderivative is just 1/3 x cubed, just like you would think. Straight out of single variable calculus. Is that cool? Okay. All right. One other little thing I want to point out, and this is just it's really a suggestion more than anything else. But here's another common mistake that students make. We're doing the x integral first. X goes from 0 to 1. You write down the numbers 0 and 1, and as you evaluate this antiderivative at these values, for example, let's plug in 1. You plug in the 1 into there, fine and dandy. You plug in the 1 into there, cool. And then a lot of students kind of forgetting which variable is playing what role at this stage. A lot of students will mistakenly then also plug in 1 for y. Which again, of course, you shouldn't do. Y is not the variable. Y is a constant as far as that integral is concerned. So y just stays y. You don't plug in for it because it's not the variable. Now, how are you going to remember not to plug in this value for the y? My little trick for this, very convenient, is to explicitly write x equals 1 and x equals 0 for these bounds, just as a visual reminder that x is the variable into which I'm plugging these values. Everybody see the idea there? Now, you don't have to do this. It's not wrong if you don't do it. But it is precarious if you don't do it, right? And don't say I didn't warn you. So if I were to not do this at all, right, and just put 0 and 1, notice, based on what's written down here, nothing in what's written down in blue there says x. You have to remember from the previous equation that x is what you're plugging in for. Again, you can do that if you want, but my gosh, it only takes a second and a half to write down x equals. Right? It's very, very quick. And it's a nice little reminder. It saves you risk of oops, which translates to points, right? And I think it's a second and a half well invested. So I strongly encourage you to do that. Okay, how are we doing? Everybody all right? Okay. This integral, truly a single variable integral. Y'all know how to do single variable integrals. Boom, answer, done, victory. And we have computed now the volume under the graph as that value. Okay. Right. So, next observation, I kind of hinted at this before, but you can slice in the other order. Previously, we did y slices. We computed the cross-sectional areas for those y slices with x integrals on the inside. That gave us this iterated integral. But you can slice the other way. I'm going to leave the details as an exercise for y'all. I think this is a very healthy exercise. It's a good learning tool to just imagine that you are instead slicing like this. That you have slices that look like that, for certain values of x. And then you're doing an integral as x goes from a to b, and then you'd be computing your cross-sectional area here that cross-sectional area would be computed as an integral as y goes from C to D. You're going to have a different picture. You can see it's going to look a little different. You're going to write down a bunch of algebra that's going to look kind of like this, except everything's a little different, right? What I encourage you to do is to use this as a guide, right? And think through, write the algebra, draw the diagrams, right? Make a completely equivalent argument with the slicing going the other direction, again, using this as your guide. And what you're going to find is that this volume that we just got through computing as what you might call a dx dy iterated integral, that volume can just as well be computed as what you might call a dy dx iterated integral. Yes?
Those volumes are the same.
Yeah, that's right. That's exactly right. So that's the whole point here, is that it doesn't matter which one of these arguments you make. This iterated integral, computing the exact same volume. Yeah. All right. Okay. So please do take the time to think through those details. It's good, healthy exercise. If you get stuck, if you're not sure, if you're confused as to, wait a minute, I thought what's such and such a variable was supposed to be a constant. Feels like from my diagram that it's not. What did I do wrong here? You get confused at any point, come to my office hours. I'll be very happy to explain. We'll work it through. But of course, you also have the help room, other instructors, office hours, all that good stuff. Okay, real quick warning. We are currently working only with rectangles. We will eventually be describing these kinds of integrals for domains that are not rectangles. A lot's going to change when we do that. And roughly speaking, this result only works when your domain is a rectangle. So weirder things happen for non-rectangular domains, and that'll be a subject for Friday. Do notice, by the way, that the x bounds being a and b when x is on the inside. Notice that the x bounds when x is on the outside, still a and b. So the way I like to hand gesture this is if you have your two differentials and you're entertaining switching your two differentials, and of course you also have your bounds over on the other side, just don't forget that when you switch your differentials, you also have to switch your bounds, because the x bounds are the x bounds, whichever way you slice, and the y bounds are your y bounds, whichever way you slice. So you cannot just do this. This does not work at all. You cannot just trade your differentials and just not trade your bounds. That does not work. Okay. Okay. Now here's some bad news. We're going to identify a problem here, and then on the next page we're going to start creating a solution to that problem. But let me remind you, in single variable calculus, we computed a bunch of different things with integrals, right? I mean, the big one that everyone likes to, lean on as a favorite example of a single variable integral, area under a curve, right? So single variable integrals compute area under a curve. But there's also the amount of work that it takes to perform a certain physical task you compute with a single variable integral. The amount of mass in a one-dimensional rod you compute with a single variable integral. Various other, the population of bacteria in a petri dish you compute with a single variable integral, et cetera, et cetera. Okay, wouldn't you think then that if we compute volume under a graph with an iterated integral, wouldn't you think, by analogy with what happened in single variable calculus, wouldn't you think you can compute like mass and population and all sorts of other things also with iterated integrals? I mean, it worked in single variable calculus that the same kind of integrals allow you to compute multiple different things. Seems like this ought to work too. And the problem is it doesn't. The argument doesn't make any sense. The argument doesn't hold water. And let me try to walk you through why that is. Keep in mind as you're computing this integral, the first thing you have to do is compute the inside. Keep in mind that the whole point of the inside here is that what we've got is a height being multiplied by a length to produce, height times length, which is area. And the whole idea, of course, of this single variable integral on the inside is that adding up these little pieces of area gives me my total cross-sectional area, which I then can integrate dy. So area is what I have. It's what I get when I multiply height times length. Area is a pre-existing geometric idea that we understand. I say that the total area is the sum of all the little slices of area because I can see pictures of it. I can look. I have a picture right here. Right? This total area is the sum of these slices of area because picture. Look at there it is, and of course it is. Right? So we're relying heavily on the fact that we understand area intuitively. Okay. All right, now let's look at the analogous part of the argument here over when we're hypothetically computing mass, for example. Well, let's look at this same kind of the first thing we have to be able to make sense out of. And what I've got, if I were computing a mass of, distributed across a two-dimensional area, density would be mass per unit area, right? If mass is distributed over area, then the density is mass per unit area. And mass per unit area times length, what is that? Right? What is this thing? I would need for this thing to be something that I already understand, that I understand how it accumulates, that the whole is the sum of the parts. I would need to know that that's the case for this. But the problem is I don't even know what this is. Mass per unit area is intended as something that you would multiply by area to get mass. I haven't done that. I've got mass per unit width as a result here. What is mass per unit width when the mass is distributed area-wise? Here's a related example. Suppose you're thinking about population. I'm sure you all know that when they talk about population and how New York City is very, very crowded. Wyoming much less crowded. Well, they talk about population density as number of people per unit area. In the sense that if you know population per unit area and you multiply by area, you get population. Great. What happens if you multiply population per unit area times length? Do I get population per unit width? What is that? How does that? People are not distributed across width. I don't know what that means. The argument fails. Right? We just cannot make sense out of this. This thing is not a thing. So I can't argue that this expression I add up for all values of x between a and b, and therefore, continue on with an argument because I don't even know what it is. I have no argument to make. This is a crash and burn. Everybody see the problem? So iterated integrals are directly connect only to volumes. And if I have any other interest, like computing mass or computing population or any actual real-world engineering or physics example, can't use an iterated integral. Doesn't work. Okay, so let's fix that. We're going to have to make a different thing. And let's see here. Let me get my glasses back on. We're going to talk about something now. Oh, wow, I'm almost out of time. Talk about something called double integrals. In order to do that, I need to remind you what single variable integrals are. Single variable integrals, very importantly, are Riemann sums. This is the definition of a single variable integral. A lot of people mistakenly think that the definition of a single variable integral is the area under a graph. This is not true, and it's importantly not true. Area is not a particularly useful concept as you're doing calculations. If I want to compute, for example, the total amount of mass distributed on a rod distributed on the x-axis, I can talk about taking that mass, chopping that mass up into little pieces, making a corresponding Riemann sum, aka integral, and I can compute that integral with the fundamental theorem of calculus. And notice nowhere in this process did I say area. And furthermore, not only do you not need area, you really can't use area because there's no immediate connection between mass, thought of as distributed across a one-dimensional rod, and area. It's a one-dimensional rod. There's no area to talk about. So this is not a natural connection. And I'm well aware, by the way, that a lot of books or instructors do try to take the point of view that you can think of mass from an area point of view. But honestly, what they do there is they point out that when you take mass, you chop it up into little pieces that you think of as density times length and interpret the density as a height, blah, blah, blah. What they're really doing there is they are kind of sloppily making a Riemann sum argument. They're arguing that mass can be computed as a Riemann sum, and the Riemann sum can be computed as an area. So, again, it remains. There is no immediate connection here. Right? So, very, very importantly, integrals have to be defined as Riemann sums so that we can connect applications to those integrals, aka Riemann sums, so that we can then compute the answer to those questions with the fundamental theorem of calculus. This is a highly underappreciated point. A lot of people think that Riemann sums are mathematician formalities that are outdated and don't need to be used anymore. Not so. Riemann sums are the link between the bazillions of applications that we want to apply calculus to and the ability to use the fundamental theorem to get answers. So area is at best a crutch. That's a nice crutch. Don't get me wrong. I like the area point of view on integrals. That's nice. It's helpful. But it's just a convenience and a crutch and I guess kind of a luxury. It's not actually part of the argument. Okay, and I'll bet you I'm out of time by now. Yeah, sorry, but I went a little over. So, okay, we're drawing a line right here. We will pick up here on Friday. Y'all have a good rest of your Wednesday. See you later. Oh, and of course, as usual, if I didn't get you down for attendance, make sure you